Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine something for a second. You are sitting in a room. It is completely silent, and it is pitch black.
Sounds relaxing, honestly.
Well, wait, because you can't see your hands in front of your face. You're just sitting there waiting. And then, out of nowhere, you hear it. A tap.
Okay, less relaxing now.
Right. A rhythmic, powerful, distinct tap. It echoes through the dark. And then, just nothing. Silence again.
Wow.
Yeah, so you wait. An hour or so goes by, and just as you're starting to doubt you ever heard it at all, there it is again. Tap. Exactly the same acoustic signature.
So you know it wasn't just your imagination.
Exactly. You don't know what is making the sound. You don't know where it's coming from, other than it sounds incredibly far away. But it is steady, it's persistent, and it is entirely unexplained.
That is a very visceral scenario.
I want you to hold on to that feeling, that visceral feeling of being in the dark, listening to that rhythm, trying to map a pattern onto a void. Because that is exactly the psychological and scientific reality astronomers have been experiencing for years.
When they look up at the night sky.
Yeah. Right. When they encounter these things called long-period radio transients. Okay, let's unpack this because the scale of the universe is just mind-blowing.
It really is. And the thing is, the human brain is hardwired to seek out patterns, right? So in astrophysics, a repeating pattern is usually the signature of a massive rotating engine.
Because space is usually just chaotic noise.
Exactly. Space is incredibly noisy. We are constantly bombarded by the static of supernovae expanding, galaxies colliding, supermassive black holes, tearing apart stray stars. It's a messy, violent, and honestly largely stochastic environment.
Right.
But when you are sifting through petabytes of that cosmic static and you suddenly find a clear, repeating beat, a metronome ticking in the void with mathematical precision, it completely arrests your attention.
Because it implies order.
Finding a pattern in the chaos doesn't just give us a new object to catalog. It fundamentally shifts our understanding of the physical laws governing the universe. It tells us we are looking at a machine and we have to figure out how its gears turn.
And the machine we're talking about today, these long-period radio transients, it's hard to overstate the scale of this mystery. We are dealing with incredibly strange, highly rhythmic pulses of energy firing off from remote, dust-choked corners of the Milky Way.
They've baffled the smartest people on the planet for years.
They really have. But today, the goal of our conversation is to explore a genuinely groundbreaking discovery that finally solves this specific cosmic mystery. What scientists have just uncovered is that the source isn't what everyone assumed.
Not at all.
It is actually a bizarre, incredibly violent dance between two very extreme, mismatched stars locked in a deadly orbit.
We are finally turning the lights on in that dark room you described earlier. And the implications are staggering, honestly. We are seeing a completely new mechanism for how energy is generated, channeled, and broadcasted across the universe.
Which is huge.
For decades, whenever we saw a repeating radio pulse, our minds immediately went to a very specific type of stellar engine. But this new discovery proves that the universe has more than one way to build a radio lighthouse.
It forces a complete recalibration. And for you listening right now, I want to remind you why this matters. It is so easy to fall into the trap of thinking of this as just, distant space trivia.
Right, just some stars doing weird plasma physics thousands of light years away.
Exactly, but this is the story about how we, sitting on this little rock, managed to piece together the ultimate puzzles of nature. We are looking at extreme environments that we could never, ever safely recreate in a laboratory here on Earth.
No, we'd destroy the planet if we tried.
We are talking about gravitational forces that bend light, magnetic fields that can rip atoms apart, and temperatures that defy comprehension. We use these distant systems to test the very limits of the physics that govern our own reality.
Right down to the device you're using to listen to this right now.
Yes. If the rules of electromagnetism and thermodynamics hold up out there in the most chaotic, extreme conditions imaginable, it tells us something profound about the fundamental, unbreakable structure of the universe we live in.
It is the ultimate stress test of human comprehension. We build these complex mathematical models of how the universe works based on what we can observe locally, right? And what we can simulate mathematically.
Right.
But when we observe something in the wild that flagrantly breaks our models, it forces us to evolve. And these long-period radio transients have been breaking our models for quite some time. They're a glaring reminder that our physics textbooks are still missing chapters.
Let's start right there with the stubborn mystery of these cosmic taps. A long-period radio transient is, well, it's a burst of radio waves that comes and goes, repeating over a specific time frame. But in astronomy, the word long is doing a lot of heavy lifting here.
A lot of heavy lifting.
We are talking about pulses that repeat on the order of tens of minutes to hours. Now, an hour might not sound like a long time to us waiting for a bus.
But in the context of astronomical signals, an hour-long gap between pulses is agonizingly slow. We're used to pulsars that flash every few milliseconds. An hour is an eternity.
Why is that timescale such a big deal mechanically?
The timescale is exactly what makes them anomalous. When we look at standard pulsars, which are rapidly rotating neutron stars, the rotational periods are typically measured in fractions of a second, maybe up to a few seconds.
Right.
The physics driving those emissions operates on those rapid timescales. So when you suddenly detect a radio burst that takes 20 minutes or an hour or almost 2 hours to cycle back around, you are looking at a system operating in a completely different kinetic regime.
It's the difference between the hum of a dentist's drill and the slow, deliberate rotation of a Ferris wheel.
That's a great way to put it. And the sheer rarity of these things is staggering.
Think about the Milky Way. Hundreds of billions of stars, billions of systems. And across all of that immense cosmic real estate, scientists have only ever definitively found about a dozen of these long-period radio transients. Just a dozen.
That statistical scarcity is a massive red flag in astrophysics.
How so?
Well, if a phenomenon is a natural consequence of standard stellar evolution, like if it's just something stars do when they reach a certain age or mass, you expect to see it everywhere. You expect to find thousands of examples.
Because there are billions of stars.
Exactly. Finding a dozen tells you one of two things. Either this event requires such an incredibly specific, improbable set of overlapping circumstances to occur that it almost never happens, or our telescope technology has been so biased toward finding fast signals that we've been blind to the slow ones.
Because they are so rare, the scientific community had to come up with a suspect. They needed to explain what was making the noise. And for a long time, the prime suspect was a neutron star. Specifically, they thought these were just very, very slow-spinning pulsars.
It was the path of least resistance, conceptually. A neutron star, as we know, is the ultra-dense collapsed core left behind after a massive supergent star detonates in a supernova.
And they spin very fast initially.
They possess incredibly intense magnetic fields, and they spin. That rapid spinning generates a massive electric field that rips particles off the star's surface, accelerates them to near-light speed, and produces beams of radio waves out of the magnetic poles.
Like a lighthouse.
Yes. If those beams sweep past Earth, we see a regular rhythmic pulse. The pulsar model is the classic rhythmic signal generator in astrophysics.
It makes logical sense as a starting point. If you hear a repeating signal, you assume a pulsar. Like if you hear galloping, you assume a horse, not a zebra.
Exactly.
But the pulsar theory completely falls apart when you look at the math for these specific long-period transients. Current astrophysical models dictate that neutron stars rotating this slightly simply cannot physically produce these signals.
So why does the speed matter so much? What is actually failing mechanically when a pulsar slows down to an hour-long rotation?
The failure mechanism is something astronomers call the death line.
The death line. Sounds ominous. It is for the pulsar. A pulsar's ability to emit radio waves isn't just a passive glow. It is an active kinetic engine. It requires a tremendous amount of rotational energy to power what we call the pair production cascade in its magnetosphere.
Okay, what is a pair production cascade?
Essentially, the spinning magnetic field creates a voltage drop. If the star spins fast enough, the voltage is high enough to pull electrons off the surface and slam them into the magnetic field with such force that they create electron-positron pairs.
Wait, like creating antimatter?
Yes, which in turn create more pairs, leading to an avalanche of charged particles that generate the radio beam. But the energy for all of this comes directly from the star's rotation. It acts as a massive flywheel.
And as it ages, it slows down.
Right. As the pulsar ages, it loses energy and slows. When the rotation drops below a certain critical threshold, when it takes longer than a few seconds to spin once, the voltage drops too low. The spark fails.
So no more cascade.
The pair production cascade ceases entirely. The pulsar crosses the death line and goes radio quiet. A neutron star taking an hour to spin once simply has no mechanism to generate the necessary voltage to broadcast a beam across the galaxy.
Okay, this raises an important question, and let me push back on this a bit, because this touches on something that frustrates me about the history of this mystery. If the thermodynamics and the electrodynamics are that clear...
Yeah, are very clear in the models, yeah.
Right. If the established models show that a slowly rotating neutron star physically cannot generate these signals because it crossed the death line, why on earth was that the leading theory for so long?
It's a fair question.
Were we just trying to jam a square peg into a round hole because pulsars are the only radio-emitting objects we understand well? It feels like, I don't know, lazy science to ignore the math just because you don't have a better idea.
I wouldn't call it lazy science. I would call it Bayesian conservatism.
Okay, what does that mean in this context?
The scientific process, particularly in a purely observational field like astronomy, relies heavily on establishing priors. When you are confronted with a completely new phenomenon, your first logical step is always to test whether an extreme version of a known object can explain it.
So you stick with what you know first.
Yes. The pulsar death line is a hard thermodynamic wall in our current models, but models are constantly being revised. Some researchers legitimately thought, well, perhaps our understanding of the death line is wrong. Perhaps in extreme magnetic environments, the cascade can sustain itself at lower speeds.
They were testing the limits of the pulsar theory.
They were testing the elasticity of the model, yes. The alternative was to invent an entirely new class of celestial object or a completely unproven emission mechanism from scratch, without any direct observational proof. You exhaust the known anomalies before you invoke the unknown.
I see your point. It's like hearing a strange mechanical grinding noise in your car. You assume it's the transmission or the brakes, even if the sound is slightly off from what you'd expect, because cars have transmissions and brakes. You don't immediately assume someone has installed an experimental alien engine under your chassis while you're asleep. You go with the parts you know exist until the mechanic proves it's impossible.
Precisely. You exhaust the known components. But in the case of long-period transients, the pulsar theory was stretching past the breaking point. The physics simply refused to align.
The brakes and transmission theory was mathematically untenable.
It was a dead end. The field was stuck in a holding pattern. The signals kept arriving, mocking our models, and nobody knew what was sending them. They desperately needed a completely new type of engine to explain the data.
Which brings us to the breakthrough, the moment where the field pivoted from a stalled mystery into a paradigm-shifting discovery. And the human element of this is fantastic. This research was led by Covey Rose, a PhD student.
Yes, at the University of Sydney School of Physics and CSIRO.
We so often picture massive breakthroughs coming from veteran scientists with decades of tenure. But here you have a student leading an international team to solve a years-long mystery, looking at the failing pulsar models and realizing they needed to rethink the entire architecture.
The history of astrophysics is actually full of these moments where students or early career researchers make the vital connection. Jocelyn Bell Burnell was a graduate student when she discovered the very first pulsar in 1967.
Fresh eyes are crucial.
They are. They are often less encumbered by the orthodoxies of the field. Rose and his team didn't just accept the slow pulsar hypothesis. They rigorously analyzed a specific target to see what else could possibly generate that kind of energetic signature.
And that specific target is a system named ASCAP J17455051. I know we love our alphanumeric soup in astronomy.
It rolls right off the tongue.
It really does. But this specific string of letters and numbers is cementing its place in astrophysics history, because for the very first time they were able to definitively pinpoint the exact origin of one of these mysterious long-period signals.
They confirmed the source.
They didn't just model it, they observed it across multiple wavelengths and confirmed it, and they found it was not a solitary neutron star gasping past the death line. It was a cataclysmic variable, specifically an accreting white dwarf star.
The identification of ASCAP J17455051 as an accreting white dwarf is the linchpin. It completely rewrites the mechanism. We move from an isolated object spinning in a vacuum to a dynamic, interacting binary system.
2 stars instead of 1.
Yes. The energy source shifts from rotational kinetic energy to gravitational potential energy and accretion dynamics. It provides a physically viable engine that doesn't violate the thermodynamics of the pulsar death line.
Let's talk about the specific phrase Covey Rose used to describe this discovery, because it's a powerful framework for everything that follows. He called this system a Rosetta Stone for long-period radio transients.
It is a profoundly apt analogy. The original Rosetta Stone, the archaeological artifact, featured the exact same decree inscribed in 3 different scripts: ancient Greek, Demotic, and Egyptian hieroglyphics.
Right, and before they found it, hieroglyphics were a total mystery.
An entirely untranslatable code. Scholars could look at the symbols, categorize them, but they couldn't read the language. But because they could read the ancient Greek portion, the stones served as a direct structural translation key.
They mapped the known onto the unknown.
Exactly. They unlocked the history of an entire civilization.
And applying that to ASCAP J17455051, we've had this catalog of a dozen or so long-period transients blinking at us from the dark. We knew they existed, we could measure their pulse rate, but they were an untranslatable code.
We didn't know the physical language of the object producing them.
Right. But this newly verified system acts as our structural reference point. It gives astronomers the translation key to look at the other dozen mysterious transients and determine if they are white dwarf systems or something else.
Now that we know definitively that ASCAP J77455051 is an accreting white dwarf, and because the team meticulously recorded exactly what its radio and X-ray emissions look like, we have a template.
So we can look back at the old data.
Yes, we can take that precise template, its specific spectral signature, its time delays, and apply it retroactively to the archival data of the other transients. Are they speaking the language of a magnetic white dwarf? It provides the foundational grammar required to categorize an entirely new class of astronomical events.
So it's like we've been hearing a weird engine noise in the distance for years, and we finally found a car pulled over with its hood popped open. Now that we can actually look at the mechanics, we can identify that exact same noise whenever we hear it on the highway.
That captures the essence of observational astrophysics perfectly. We have finally popped the hood on the specific cosmic engine. We're no longer debating abstract theoretical physics regarding how a dying pulsar might behave. We have direct confirmation of an active binary accretion engine.
And what an engine it is! Now that we've popped the hood, it's time to examine the actual moving parts. What exactly is a white dwarf, and what is it doing to its neighbor? Because the anatomy of this bizarre stellar dance is wild.
It really is.
It's a binary system, meaning 2 stars locked together by gravity. But they are an incredibly mismatched pair. Let's look deeply at the physical characteristics, starting with the white dwarf.
The drastic disparity in their physical characteristics is the entire reason the system is so dynamic and violent. The primary star is a white dwarf. A white dwarf is a stellar remnant, the exposed, collapsed core left behind after a main sequence star has burned through its nuclear fuel.
It's basically a dead star.
It is no longer undergoing nuclear fusion. It is essentially a glowing ember cooling down over billions of years.
But the scale of that ember is what breaks the brain. This white dwarf is roughly the size of the Earth. The physical volume it takes up in space is comparable to our own tiny planet. Yet it contains a mass that is close to that of our entire sun.
The density is astronomical, quite literally. You have to imagine taking roughly 330,000 Earths, which is the mass of the sun, and crushing all of that matter down into a sphere the size of a single Earth.
I can't even picture that.
The atomic structure itself breaks down. The electrons are stripped from their nuclei and forced into a degenerate state where the quantum mechanical resistance of the electrons being squeezed together is the only thing preventing the star from collapsing further into a black hole.
Oh, wow.
Because it is so massive and so compact, the gravitational pull at the surface of a white dwarf is hundreds of thousands of times stronger than Earth's gravity. A single teaspoon of white dwarf matter would weigh several tons.
So you have this tiny, ultra-dense, immensely heavy powerhouse, and orbiting it is the companion star, a red dwarf. The contrast here is almost comical.
It's quite extreme.
The red dwarf is physically larger in volume than the white dwarf. It takes up more space, but it is incredibly low mass. It only has about 1/10 the mass of the sun.
Red dwarfs are the most common type of star in the universe. They are cool, dim, and have very low density compared to a white dwarf. So you have a situation where a physically smaller object exerts a vastly superior gravitational dominance over a much larger, highly diffuse, lightweight object.
And they aren't just neighboring stars drifting past each other. They are locked in a violent, incredibly tight orbit. A full orbit takes just over an hour, 1.4 hours to be exact.
Think about the orbital mechanics involved there. You have 2 stellar bodies whipping around a common center of mass in less than 90 minutes. The distance between them is incredibly small, likely less than the radius of our own sun.
That is Terrifyingly close.
At that extreme proximity, the gravitational forces are not just holding them in orbit, they are physically distorting the structure of the stars. The immense gravity of the white dwarf stretches the red dwarf into a teardrop shape.
Which brings us to the cataclysmic part of the cataclysmic variable. The accretion process. What is actually happening during this 1.4-hour sprint? The dense white dwarf is actively shredding and pulling material away from the larger, lighter red dwarf.
Because of that extreme proximity, the red dwarf actually expands beyond what astronomers call its Roche lobe.
The Roche lobe?
It's essentially the gravitational boundary around a star in a binary system. If the star's material expands past that invisible boundary, the gravity of the star is no longer strong enough to hold onto it.
So it just spills over.
The material crosses the inner Lagrangian point, the point where the gravitational pull of both stars cancels out and falls into the gravity well of the white dwarf. The dense white dwarf is actively shredding the red dwarf. It is siphoning hydrogen and helium plasma away from the outer layers of its lighter companion.
Here's where it gets really interesting to me. Trying to visualize this, it's like pairing a dense bowling ball with a massive, fluffy cotton candy sphere.
I like that.
Even though the cotton candy is bigger, taking up more space on the table, the bowling ball's gravity is just relentlessly peeling away layers of the sugar as they spin around each other in a dizzying 1-hour circle.
The cotton candy analogy is effective for visualizing the density contrast, but we must refine the mechanics of the peeling. The word accretion can sometimes sound gentle, like dust gathering on a shelf.
This is not gentle.
This process is anything but gentle. It is a violently chaotic, spiraling transfer of plasma. Because both stars are orbiting so rapidly, the material ripped from the red dwarf possesses a massive amount of angular momentum. It cannot fall straight down onto the white dwarf.
So what happens to it?
Instead, it spirals inward, forming a massive, incredibly hot, swirling vortex of gas known as an accretion disk around the white dwarf's equator.
A swirling vortex of gas. And that transfer is the foundational energy source for the signals we detect.
Exactly. And the fluid dynamics within that accretion disk are ferocious. The inner layers of the disk are orbiting much faster than the outer layers, creating immense viscous friction. This friction acts like a cosmic brake, slowly bleeding off the angular momentum of the gas, allowing it to spiral further inward.
And friction means heat.
An astonishing amount of heat. The inner regions of the accretion disk can reach temperatures of millions of degrees. This violent shredding, spiraling, and frictional heating process is the engine powering the entire system.
So, with this violent shredding process established, how does this physical transfer of matter translate into the specific rhythmic radio and X-ray pulses hitting Earth? Let's get into the mechanics of the signal, because it's a dual emission.
This is where the observations elevate from interesting to groundbreaking.
They observed a 1.4-hour cycle of powerful radio wave and X-ray bursts. ASCAP J1745-7051 is only the second known long-period radio transient to emit regular X-rays, and crucially, it's the first where the cause of the regularity has been confirmed.
The confirmation that the X-rays and the radio waves are both locked to the 1.4-hour orbit is the vital clue. It proves that the emissions are not random flares. They are a direct consequence of the physical, clockwork rotation of the binary system.
So let's trace them, starting with the X-rays. We talked about the millions of degrees in the accretion disk. How are the X-rays born?
As the material from the red dwarf is drawn toward the white dwarf, it gets caught on the white dwarf's powerful magnetic field lines. It's channeled directly toward the magnetic poles.
It's like water down a drain.
Yes, a funnel flow. The plasma accelerates along these lines, reaching velocities of thousands of kilometers per second. When this supersonic stream of plasma finally smashes into the surface of the white dwarf, it creates a massive accretion shock.
Wow.
The kinetic energy of that impact heats the plasma to tens of millions of degrees, emitting copious amounts of high-energy X-rays. So the X-ray pulses are the direct thermal signature of material physically slamming into the white dwarf.
Okay, so that's the X-rays, but what about the radio waves? Where do they come from?
The radio emissions occur where the magnetic fields of the two stars meet and interact with the charged, ripped material.
High up in the magnetosphere.
Exactly. Within this turbulent magnetic environment, highly charged electrons are accelerated to near the speed of light. When they spiral rapidly along strong magnetic field lines, they emit intense radiation in the radio frequency range.
And it gets focused.
Yes, the geometry of the magnetic field acts like a waveguide. It forces the radio emission to be tightly beamed into a cone. It produces a focused searchlight of radio waves.
And this is the crucial part, the time delay clue. Covey-Rose's observations showed that the radio and X-ray signals do not peak at the same time. There's an offset.
What's fascinating here is the significance of the delay. If the X-rays and the radio waves were being produced at the exact same physical location, you would expect the photons to arrive simultaneously.
But they don't.
The fact that there is a distinct, measurable delay between the arrival of the X-ray flash and the arrival of the radio burst is the ultimate clue. It definitively proves spatial separation.
They are produced in completely different regions of the binary system.
Yes. The X-rays are originating from the ultra-hot shock right at the surface. The radio beams are generated much further out in the complex magnetic zones. Yet they are both entirely synchronized by the overarching orbital motion.
Which raises a big question for me. If these two stars are surrounded by a chaotic storm of shredded plasma and magnetic fields, how does the resulting radio beam stay so tightly focused and strictly scheduled to this 1.4-hour cycle? Is it acting like a lighthouse beacon sweeping past Earth?
The lighthouse analogy is structurally accurate, but it's a lighthouse constructed out of unyielding orbital and rotational mechanics. The chaos of the plasma is immense, yes, but it is ultimately subservient to the rigid laws of angular momentum.
Because the white dwarf is so heavy.
Exactly. It possesses immense mass and rotational inertia. It acts as a massive, stable gyroscope. No matter how chaotic the infalling plasma is, the white dwarf's rotation rate remains incredibly steady.
So as the star turns, the beams turn with it.
Precisely. The orientation of that magnetic field structure changes exactly in step with the rotation, sweeping that tightly focused radio beam across our line of sight with mechanical regularity.
That is just wild to think about. To capture such specific offset signals from a chaotic environment tens of thousands of light years away requires unparalleled technology and international teamwork. Let's talk about the natural laboratories and global eyes that made this possible.
The universe provides these extreme natural laboratories, but they are entirely invisible to us unless we build the instruments capable of detecting them.
And the primary tool here was the ESCAP radio telescope, owned by CSRO, located out in Western Australia. It has this unparalleled mix of coverage, resolution, and sensitivity. Why is this specific telescope so perfectly suited for hunting these rare transients that others missed?
Well, a transient is unpredictable. You don't know where it's going to flash or when. Older telescopes were like trying to photograph a lightning bolt with a microscopic zoom lens.
Great resolution, but you're only looking at a tiny patch of sky.
Exactly. You miss almost everything. ASCAP changes the paradigm. It uses something called phased array feeds, or PFs.
What do those do?
A PA acts like a high-definition, multi-pixel camera for radio waves. It allows ASCAP to synthesize up to 36 separate simultaneous beams on the sky. It casts the widest possible net with the finest possible mesh, giving it a massive field of view.
So it can survey vast swaths of sky and catch that unusual slow-beating signal. But it wasn't just ASCAP. This required a massive international collaboration.
It really did.
They had astronomers from the US, China, Canada, Spain, Israel, and Australia. They used the Australia Telescope Compact Array, South Africa's Meerkat, the Aurorar and Magellan optical telescopes in Chile, and space-based telescopes like Swift and Einstein Probe.
Coordinating a multi-wavelength observation campaign of that scale is a monumental logistical challenge. But it was the only way to solve the puzzle. You need radio for the magnetic fields, optical for the star structures, and X-ray for the thermal shocks.
It's the first system where we can clearly see both stars and the accretion process in action.
And if we connect this to the bigger picture, we aren't just solving a space puzzle. These systems are natural laboratories. They allow us to test our understanding of extreme plasma physics, strong magnetic fields, and intense gravity.
Conditions we absolutely cannot replicate on Earth.
No. We are testing the fundamental laws of physics against the most extreme stress tests the universe can provide.
So what does this all mean? By combining a cutting-edge telescope in the Australian outback with space-based X-ray satellites, humanity has managed to peer into a distant cosmic blender and map out exactly how it works.
It's a monumental achievement in observational astronomy. We moved from an impossible pulsar to a perfectly mapped cataclysmic variable.
To briefly recap this incredible journey, we went from unexplained, rhythmic cosmic taps in the dark to the discovery of a dense white dwarf aggressively pulling apart its red dwarf companion,
creating a synchronized lighthouse of X-rays and radio waves.
And it serves as a Rosetta Stone for astrophysics. For you listening, I want you to consider what other mysteries are hiding in plain sight, waiting for the right tool to decode them. Science is an ongoing process of discovery, driven by curiosity and collaboration.
It's a dynamic process, constantly revising its models. This Rosetta Stone is a beginning, not an end.
Which leaves me with a final, lingering question to ponder. If this single system serves as the Rosetta Stone that translates the other dozen known long-period transients, what happens if the translation reveals that not all of them are white dwarf systems?
That'll be something.
If some remain untranslatable, even with this new key, could there be a third, entirely unknown class of celestial engines out there, quietly tapping away in the dark, waiting for us to realize our physics models are incomplete yet again?